Welcome everybody on Zoom, welcome everybody in the lecture hall. Today, I will make sure to answer any questions that you might have on MapReduce to make absolutely sure that you're following, because at the end, when I check, it seemed to be rather on the slow down side. So I'll make sure that everything is clear. You will see that then when we go on Spark, it will be more practical. So that will be on the easier side. What I wanted to clarify first is this whole thing about splits, tasks, slots, and phase. To make absolutely sure you understand this, this is fundamental for the physical layer of any parallel processing system. It's in MapReduce, it's also in Spark, it's in almost any system you will ever see. This is actually called also batch processing. It's a form of batch processing. I will take a real life example, actually, just like the Pokemons, but with postcard signing this time. The thing with the Pokemon example was that there were as many tasks as slots. There were 10 students, but also 10 batches. So this is maybe what wasn't clear. So I'm going to show you another example where, like in real life with MapReduce, there are actually more splits and tasks than there are slots. So imagine you probably already did that. You're with your friends, you have to send, I don't know, wedding invitations, postcards, and so on. So let's say you need to send 50 postcards from your vacation, and there's 3 of you. And even though one of them has extra help, and you need to take care of these 50 postcards. So the first thing that you do, and I'm sure you already did it in real life, is that you make batches of these postcards, right? So you take 10, 10, 10, 10, 10, there's 50, so you make 5 batches. These are the splits in MapReduce. This would be the splits, right? Each split partition has 10 postcards, and let's put numbers on them, 1 to 50, so 1 to 10 in the first split, 11 to 20, and so on. These are the splits. So what are the tasks? That's easy. There is one task for every split, right? There is task 1 that consists in taking care of the first split. So this is write whatever or sign on postcards 1 to 10. Then task 2 is split 2, right? You write on the postcards 11 to 20, all the way to task 5, which consists in writing on postcards 41 to 50. For whom is that clear? Right? These are the splits. There are always as many tasks as splits. The split is the data itself. It's a chunk or partition of the data itself. The task is the assignment. It's a to-do. You have to do that. You have to write on the postcards 1 to 10, for example. This is a task. Now, there are 3 groups. These are actually the slots, right? This is whoever takes care of the tasks. In the case of a cluster, it's the CPUs and the memory. Here, it's people. So we have 3 people who are going to take care of that. So what do we do when they start? So they each pick 1 task each, right? So 3 of the tasks are going to be assigned when we start. And then they start working on their tasks, you know, sequentially. Right. So, for example, the person on the left will take the first postcard. She's going to write something on it. Then she takes the second postcard, then write something on it. So it's sequential, right? You cannot. I don't know. I'm not able to basically write with my 2 hands on 2 different postcards, right? So this is why it has to be sequential. But what is in parallel is that the persons, they are around the table doing things in parallel, right? So they write at the same time. Now. The person in the middle has extra help and is able to finish earlier than other people. So she's done with the 10 postcards. What's going to go on? The others are not done, right? Well, this is exactly like you probably did it in real life. She just takes another batch of postcards and continues, right? So now this is task 4. And she starts writing on postcards 31 to 40, also sequentially. And you notice that task 2, then task 4. There was also sequential in here. Then the guy on the right is done too. Oh, that's just Zoom acting up, but I continue. So he's done. So he takes task 5, right? That was still undone. So takes the next 10 postcards, works on it. Then in the middle, they're incredibly fast, so they're already done with everything. So what's going on now? There's no more tasks, so they're waiting. They're just idle, right? Maybe they're going to get some coffee or whatever, but they are just idly waiting for the other 2 to complete. Now, the person on the left is done as well, so she also waits. So now you have the first 2 groups are idle, and then the only person left, sorry, is on the right, and then he's done as well, right? And then this is it, you are done. So what do you have? You now have the output in 5 batches of 10 fully signed and written postcards. For whom is that clear? Who sees the direct relationship now with CPUs, memory, slots, tasks, and splits in MapReduce? This is exactly the same thing. And the same thing goes in the map phase, and the same thing goes in the reduce phase. No matter what phase you're looking at, it's always, always, always working that way. And I think the one thing that I forgot to say last time that wasn't clear is there are more tasks than slots. This is why you just keep spreading the tasks for as long as there remain tasks on the slots. And then when they are done and there's no more tasks, they start idly waiting, and then everybody's done and this is complete. Okay. So I wanted to clarify that, and now I'm going to take questions. I already see 2 questions, so I'm going to take one by one. So yes, we can do the catch box.
Does it work? Yeah. So do we have to give the, so I think in the other model we had yesterday, we basically, once we know one container is done, we can give it another task. So basically we can do this on the fly, basically. We say, okay, this is idle. Then we can already give it to them, and we don't have to like because here it's kind of here it was kind of predetermined who gets which tasks, but that does not have to be the case, right?
Exactly, it's not predetermined. Okay. What's predetermined is the tasks themselves. What is predetermined is that in task 1, this is about postcards 1 to 10. So every task knows exactly what's going on in the task, but the mapping between the slots and the tasks is not predetermined and is dynamic. It's very important because imagine it's predetermined and you say in advance that it's 2 here, and 1 here. What if then somebody is super slow and everybody else wait for them, right? So the reason you do it dynamically is precisely to allow that when somebody does done earlier, they will have more tasks because they will just happen more often, right? So this is why you really, really do that dynamically for as long as there are tasks, you keep spreading them, and at the end they wait.
Yeah, and I have another question regarding Yarn.
Yeah.
So when we did Yarn, the lifecycle management, I think it said in textbook that basically after the map phase is done, we basically close the mapping, like the containers responsible for mapping, and then basically petition the resource manager for another containers for reducing. Is there a way to not, like, because that's overhead, right? I mean, obviously sometimes reduce containers might like need different resources, right? They might need like more CPU or whatever. But is there a way to just keep that? Because I think that like often that's might be useless overhead, right? If you already have 10, why do you need to close them?
So I didn't fully understand the question. I'm just commenting on the first part that you said. You need to keep the containers for the maps alive until the shuffling is done, right? Because you still want to preserve the data to shuffle. So there is a moment where you have both the reduce containers and the map containers, and you ship over the thing. Yeah.
What I'm asking is basically whether it's possible to reuse the map containers as reduce containers, because like, why do we need new containers? Obviously they might need different resources, but if they don't, can we just keep them?
That is a very good idea. In fact, so this would be independent from Yarn, right? Yarn actually doesn't care, right? For Yarn, it's a black box. The application master does what he wants. But you could imagine an implementation of MapReduce, and it might actually be they tried it, or who knows, where the application master decides to reuse the same containers for the reducing, right? It might be that you could optimize that, but you have now to understand that this is a compromise with the modularity and the simplicity of implementation, because setting up brand new containers assigned to reducing is easier than writing all the logic to actually move over a container that was doing mapping to reducing while handling the shuffling at the same time. So here it would be the complexity. I'm not saying it wouldn't work. It might be that you can do that and it's faster. I also don't know if the overhead would be worth it, what you fix, because what's really taking time here is the shuffling. And it's not necessarily the creation of the reduce container. Also, you can start creating the reduce containers earlier, right? Than is done. And finally, to complete the answer to this question, you also need to consider that in a typical company cluster, you're not the only user of the cluster. Right? The entire company is on the cluster. So what you have is a tiny part of the cluster. So once you understand that, the actual cost of creating new containers and then throwing away the old ones is exactly the same. This is the elasticity of the cloud, right? You just trigger machines and so on. But since what you pay is based on machine hours, right? It's the same to use one machine for 2 hours or 2 machines for 1 hour and so on. So in terms of utilization, it doesn't make a big difference, right? But these are very interesting questions to ask, to reason in that way, right? Did I answer?
Yeah. Perfect.
Okay, awesome. So now we can go over there. If you can throw. Wow. Oh, okay. Was it a laptop? Oh, I hope it's okay. Okay, good. Go ahead.
Yeah, so I wanted to ask, these slots map to threads on the nodes, right? So it in a previous schema, you showed us that one node can have multiple threads, like multiple reduced threads, multiple map threads. So then it can happen that we have parallelism on the same node, as in two threads or two slots are running at the same time, right?
Yep.
Yeah. Okay.
So I can comment on that. So a slot, in the way that I explain it, and in this sense, is a thread, right? Each person here would be the equivalent of a thread. What happens, of course, you know that machines have multiple cores, right? So if a machine has 8 cores, then you can efficiently run 8 threads naturally. In fact, because of hyper-threading, you can even run 16, right? You can, in fact, double the number of cores because of the hyper-threading that you have in the CPU. So basically, just because you have multiple cores already means that you will have several slots on the same machine, right? So you might have 16 slots on exactly the same machine, right? Now you need to understand how the containers play in what role they play in that picture, because the container might have multiple cores, right? In that case, that means that the container has also multiple slots, right? Right. So you might have, for example, one big container there that has 3 virtual cores, and then you have 3 threads and 3 slots in the same container. So the container is an abstraction that is in between the notion of slot and the notion of machine, right? So you have the slot that is the thread. You have the container that is a process that can have multiple threads and multiple slots. And then you have the machine, which can be running multiple processes at the same time, right? So there's really 3 levels: the slots, the container, and the nodes, the machine. Does it help?
So I'm confused. We can have even multiple slots on the same container?
Yeah.
Okay.
I will come back to that in the case of Spark, actually. In MapReduce, it's not explicit. In the case of Spark, it is explicit. I will have slides on that, either today if we have enough time, or next week, but I will explain all that. Because in Spark, you actually have full control of that. You decide how many cores you have in every container, right? So now you could ask, okay, why would I have one container with 16 CPUs rather than 16 containers with each one CPU, right? That's a totally fair question to ask. And the difference between the two is that you share the memory within a container. It means that if you have 16 containers of one core, they each have their own exclusive memory. If you have one container with 16 cores, 16 slots, they share the memory. Sharing the memory is a benefit, because if you have exclusive memory and many of the slots are not fully using the memory, but one of the slots needs more memory, then they are stuck because they are still limited with the memory they have. But if you have one container with 16 slots and one of the slots needs more memory than the others, this is all fine because the memory is shared. So they can just go on and use different amounts of memory as they see fit, right? Does it make sense? Right? I'll come back on that, right? I will have slides on Spark. I will show you on the command line how you can specify the number of containers you want, the number of cores per container, the amount of memory per container. This is all configurable on the command line, right? Is it okay? Okay. And don't hesitate if you have more questions to ask, and I can go in more explanations.
Yeah, question.
Oh, yeah, go ahead.
Question is, how does Yarn solve this unfungible issue? And by unfungible issue, he means when a machine finishes and there's no more tasks, does it just have to wait idling?
Yep.
So the container is essentially still waiting for the task to finish and cannot be used for other things until it finishes the shuffling phase.
Yeah, so that's also a good question. It will be answered in a subsequent lecture that I will spend time on that, especially on large scales. What happens is that indeed, the pattern here will always be the same. You basically are first in a cruise mode where there's always tasks. So everybody has something to do. And towards the end, you are out of tasks and then 1 will be idle, then 2 will be idle, then 3 will be idle, and then everybody except 1 will be idle, waiting for the last one, and then you are done. And in fact, we will see that in many cases, it's waiting for the last one that is the tricky part. Because what about if the last one takes forever, right? And this is something we'll look into in details very soon. Yes? Maybe we can go back. Yeah, wow.
But we could already start shuffling at that point, right? If it's all idle, I mean, we can't reduce yet, but we could already start shuffling. Probably.
Yes, this is an optimization. So indeed, you are absolutely correct. You can start shuffling. Even if you're not fully done, you could already trigger the creation of the reduce slots, and you could already start shuffling, for example, the output of the first 3 tasks. You could already ship them over. What you cannot start is reducing. Right? You cannot start reducing, but you can absolutely start shuffling. What's the worst that happens? If you lose anything, you just restart a map task and so on, you know. But shuffling, you can definitely already start proactively. In fact, there is a beautiful visual that I saw in certain companies when you actually launch a map reduce task and then you wait for 10 hours for it to complete. What the visual you have is typically some sort of, I'm going to read for those who see it on Zoom. So you basically have some sort of rectangle like that. That first feels, I can't remember the colors, but basically fully red, meaning that it's all mapping. And then you start seeing some blue coming from the bottom, which is the shuffling part. And the blue starts appearing before the red is completely done. So you start having some blue going up, but then the blue goes all the way up. And then you have the green that starts when the red is completely done. And so you have this beautiful visual of filling with red, then filling with blue, then filling with green, where you see the progress on your cluster. And if you have thousands of machines, it gives you the goosebumps, you know, like you're just sitting in front of your computer, seeing the progress being made on the cluster, right? Okay, but that's very good insight that indeed you can already start shuffling before. All right, so this is what I wanted to come back to. Any more questions? Okay, and you can also ask offline, you know, send emails, ask on the Element chat if needed. Okay, so this is what I showed you last time, the life cycle of RDDs in Spark. The RDDs in Spark, it's like the collections of key value pairs in MapReduce, right? The difference with MapReduce is that it doesn't have to be key value pairs. It's collections of whatever you want. It can be key value pairs, but it can also be something else. Can be strings, can be JSON objects, can be anything you want. So you can create RDDs, transform RDDs, I'll show you how today, and act on an RDD. Okay, what I told you is that everything is lazily evaluated, which means that you need an action to actually trigger computation. If you build a creation of an RDD and transformation and you look at your cluster, everything will be idle. There will not be a single CPU doing anything. It's the moment you trigger your action that it puts everything into motion and it starts processing. What you need to understand, we'll see later, is that there will be multiple levels of batch processing like the postcards that I showed you earlier. But this is the physical part. Here, we're only looking at the logical parts. Okay, so we have Java, Python, Scala, and I'm going to show you a very small example in Python of how this actually looks like. So in Python, you basically create some SC. It means it's a context Spark context object that basically is the starting point. And one way to create an RDD is to just generate it on the fly. So let's create a small RDD with just 2 strings. So it's an RDD of strings. It only has 2. Of course, it's just an example, right? In practice, you're going to have billions, but here it's just 2. And it's generating from your local memory of the client. So it starts with a local Python list here, and then you ship it over to the cluster with the parallelize function, and then it's going to be spread over the machine as an RDD. So this is a creation of an RDD. So I have a visual on the top, on the bottom left here, hello world, hello there. You see it's an RDD of 2 strings, hello world and hello there. And I put this in a dashed rectangle. Why did I do that? Because this is lazy. This is not actually happening yet. You do have your local Python array on your client, but you don't have yet the RDD on the cluster. So this is why the dashed lines, that is just pedagogically to tell you this is what is going to happen when it is evaluated, but in fact, it's not yet happening because we don't have an action yet. Now, let's look at a transformation. How does it look like? You take RDD1, which is your first RDD that you created lazily. And now I'm applying a transformation. It's called the flat map, but there's many others. And I will go through, it's like the restaurant menu. Again, I'm going to show you all the menu that you have at your disposal. And flat map is one of them. And the flat map, you just need a function. It's like in MapReduce, you need a map function and you need a reduce function, right? So here you need a flat map function. There's a fancy word, it's called a lambda and so on. Who knows lambdas and so on? Probably a lot of you, right? So this is basically an on-the-fly function. And it's just a function that takes a value and splits the value. So it's going to take a string and output multiple strings, splitting by space, right? So what I get then, if I draw the visual of what's going to happen, is that now I have an RDD, RDD2, with 4 strings: hello, world, hello, and there, because there was a space in the middle of each one of the original ones. For whom is that clear? Okay, who understand this flat map thing? Okay, flat map means that it's mapping 2 strings and then it's flattening everything all over again, right? So you forgot where it came from, basically. All you see is 4 strings, okay? But this is all lazy. There's again this dash rectangle right there, because actually this is not even computed just yet. This is just that I'm showing for pedagogical reasons. Now, let's do an action. The action is called count by value, and this is what's printing on your screen. So you have to count how many of each string there is. So hello, comma appears twice, the first and the third value in the RDD2. So you have key hello with a value of 2 because it's twice. There appears once, so you have there 1, and then world appears once, so you have world 1. Now the dashed lines are gone. Why? Because from the moment you pressed enter, it's the moment you press enter. It's very powerful to press enter, right? You press enter and everything gets set into motion on the cluster, and you're going to have all of your worker nodes and containers that are going to work towards generating this final result. What's very important is that what you have on the right is not an RDD. This is something you download and have on your computer screen. This is a local Python dict in that case. For whom is that clear? Okay. So as you can imagine, if the RDDs 1 and 2 have billions of items and you could have millions of keys, it might not be a good idea to press return. Because then, as you can imagine, the quantity of data that's going to be shipped to your laptop is going to be enormous. So you always have to be aware of the size of these things. And this you should do if you know that the number of keys is reasonable, that it fits in a local Python dict, right? So RDD created when you press return here. RDD created when you press return here. This is distributed over the cluster. And this is a local Python dict that you download from the cluster. Okay, who is following? Okay. So now what I'm going to do is, it's the best part, you know, when you go to a restaurant and you get the menu and then you look at all the starters and the entrees, as you say in California, and then the desserts, and you just need to pick what you want. Yes, could you please throw the catch box? Yeah.
Just a quick question. I'm not sure in the previous example, what is the key of these values? The key of hello world and hello there? Because I thought we are supposed to send key value entries to MapReduce tasks, or am I wrong in this situation?
So here it's not MapReduce, it's Spark. So in Spark, it can be key values, but it doesn't have to.
I see. Okay.
Right. So this is the difference. This is why here, the first RDD, you see, these are not key values. These are just strings.
Yes.
And this is fine. The second one, these are also just strings. So there are no key values in there at all, right? You can, however, generate key values. And this is when you do count by value, you actually do generate, you can either see that as a sequence of key values, 3 key values, or you can see it as a local Python dict.
Okay. It was my mistake, because I thought Spark is just an abstraction on top of MapReduce. Just
no, it's so this is a very good remark. Spark is not built on top of MapReduce. It uses the same ideas, this idea of batch processing and so on, but it's a completely different system. It's not even Hadoop. It's not even the Hadoop team. It's the Databricks team. So it was created at Berkeley originally. and they founded a company called Databricks and Apache Spark. Now it's an Apache project. It's open source, so it's maintained separately from Databricks. And Databricks is a distribution of Apache Spark, right? And there's other companies like Hortonworks, I think is another one. Cloudera, I think is a third one. So there's multiple distribution. It's like Linux, right? You have Ubuntu, Debian, and so on and so on. But Spark is the open source. It's totally separate from Hadoop, nothing to do with that. However, it interacts with Hadoop because you can interact with HDFS, you can with HBase and so on. Right. Yeah. So thanks for allowing me to precise that. Okay, how much time do we have? Just checking. We'll have 20 minutes. Okay. Okay, so let's look at our reference menu. So now I'm going to show you all the transformations that we have, and you will see it's much better than MapReduce, because in MapReduce, you don't have a choice. It's map and reduce. But here, you have plenty of transformations. So now I'm going to represent my RDDs. I used to represent them, if I show you, as single nodes, right? I had an abstraction that my node was my entire RDD. Now I'm going to do it differently. I'm going to use visuals by showing my RDDs as these little squares like that. So each square is a value. So I have a big RDD of values, and a transformation is a logical mapping from this top RDD of value to the bottom RDD of values. In that case, we are looking at unary transformation because they pick one RDD and give you a second RDD. Okay, here's one. This is a filter transformation. It's super easy. All you need to do is supply a predicate as a lambda. For example, it's a lambda that takes a value and returns a Boolean, true or false. So then what's going to happen is that these predicates that as a user you provide to the filter transformation is evaluated on every single value in your input RDD. Every value, you evaluate the predicates, either true or false. If it's false, you just throw it away. And if it's true, you just propagate it. So what you end up with, I was about to say a subset, but it's more like a sublist, a subsequence, in the sense that the order is actually important. So it's a subsequence of the original RDD. It's exactly the same value. You don't change them. You just let them go through and filter out the others. For whom is that here? Okay, it's just a filter. How does it look like in the syntax? Exactly like shown here. It's going to be rdd1.filter, and then in parentheses, lambda value colon, and then something that returns a Boolean, right? That's how it works. Okay, so let's look at others then. This is a map transformation. The map transformation takes a function, a lambda, that you supply on the fly, that takes a value and returns a value. That value can be whatever. It can take a string, return a date. It can take a JSON object, return an XML element. It can take a key value pair and return binary values. It can be anything. It doesn't even need to be the same type, right? So you map every value from the top RDD to exactly one value in the result RDD. Exactly one. That's very important. Exactly one. Okay. So this is the map. And again, it's just a lambda. Here it's a value returns a Boolean. Here it's a value that returns another value, possibly different type. Okay. Now, here's the one we saw, the flat map. What's the difference between the two? Well, the difference is that the function that you supply in the case of the flat map can return 0, 1, or more values. Why is it flat? Because you flatten everything. So even if you return multiple values from the same value in the original RDD, you forget where it came from. So here you for example, you had this value here that is mapped to 4 different values in the outputs. But it's not, there is no structure that says that these 4 belong together. There is nothing like that. This is why it's flat, it's flattened. So if you forgot where it came from, you don't know anymore what the boundaries were. You don't know anymore where they came from and which were together. Who understands that? The flat map, in fact, is the MapReduce map, right? So the mistake not to make is to think that this is the MapReduce map. But no, because in MapReduce, you're not constrained to return just one, right? So the real equivalent of the MapReduce map is a flat map. So if you want to emulate MapReduce with Spark, you need to use a flat map transformation with what you used as a map function in MapReduce. Who sees that? That this is the MapReduce map? Okay, awesome. Okay, here's another one. Like now we are really exploring our menu. So another transformation is called the distinct transformation. there is an assumption here. There is an assumption that you have a comparator that is able to tell you for any two values, are they the same or are they not the same? This is also something you need to supply. So the API might vary. I'm not sure it's as a lambda. It might be that in Java, for example, you need to make sure that your value class, the type of your value implements the comparator class, or that you supply somewhere a comparator function, right? But this depends on the language. In Python, in Java, it's probably done differently. But anyway, we assume we can compare. We have programmed a way to compare the values. And what Distinct is doing is that it's going to eliminate duplicates. So if it sees that there are several times a blue square, it's only outputting one, and so on and so on. Okay, for whom is that clear? This here is the distinct transformation. Okay. Here's another one. It's called sampling. This is actually very trendy in the machine learning community. Some people discovered that you can do machine learning just as well with samples of your data. So it's really what it is. You have the population, who knows statistics, population sample? Oh, okay. So you basically have a super big RDD, maybe it's billions of items on top. Item is the same as value, billion of items. And you want to select, I don't know, 1% of these values and only keep 1%. So what you need is a random function, a way of basically rolling a die. Every time you roll a die, and then there's 1% of chance every time that you keep it. It can be 1%, 5%, the user says, right? You say if you want 1%, 10%, 50%, and so on. And then there's going to be randomness, but as you know, randomness with von Neumann architectures is not true randomness. You actually have a seed that actually contains the seed of randomness. And if you actually give the seed, then it's deterministic, right? But if you generate the seed based on some random stuff like the actual time, or maybe the result of a quantum experiment or whatever, then it's truly random. Okay, but this is just the usual that you saw probably in cryptography as well. Okay. We have questions, I think, on Zoom.
Does sample guarantee to get exactly the fraction, and how?
No, because it's random, right? So all you guarantee is that you are you have some. Let me explain it differently. Let's assume we have an ideal random generator, not implemented with a seed or whatever. It's a real, fully random, maybe with a quantum system and so on, that's going to generate some random value. Then this is basically the central limit theorem. If you say I want 50% of my billion values, you can already know there will be around 500 million in the outputs, but it's never going to be exactly 500 million. Maybe it's going to be plus minus 1,000, plus minus 500. You know, there's always a margin of error because you really make a random choice. The only thing that there are theorems like the central limit theorem, there's the weak, the strong version. What it tells you is that the more you continue with more and more value, the closer you're going to get to this percentage. But it's never in practice going to be exactly that percentage, right? The word for that is typically. It's typically going to be that percentage, but not exactly. Did I answer your question?
There's a second question as well, which is, does sample transform return samples with replacement or without?
So I didn't get the second part.
Does sample transform return samples with replacement or without?
Oh, I think it's without replacement. The reason it's without replacement is by implementation, because if what you do is take one value each time and roll a die, then you're not replacing it. You're always going to the next value every time. You know the difference, right? With and without replacement. When you draw, for example, you draw balls of certain colors from a box, you can either keep the balls that you pick out from the box, you put them on the side, or you put them back into the box and you can draw them again, right? But in that case, it's without replacements, I think, the way it's implemented. So you will not get multiple times the same values in the outputs. Okay, these are good questions. Any other question? Okay. Who is comfortable now? It's quite practical, right? This thing. Okay. Now there are other transformations that act on two RDDs, right? So not just one, but actually two. An example is the union. You might have an RDD that you generated in some way on the left, another RDD that you generated in some way on the right, and you want the union of the two. So you just It's more like a concatenation, right? You just concatenate the two, right? Here you see the terminology is a bit fishy because technically union would be on sets, but there is actually an order. So, but that's just I hope I conveyed the intuition here, right? I wouldn't have called it union, I think. I probably would have called it concatenation. But anyway, that's clear, right? So this is taking two RDDs and creating a new RDD that is concatenating the other two. Now we have the intersection where you have two RDDs and you create a third RDD where you only have the values that are in both of the input RDDs, right? Do we have a question over there? No? Okay. So this is the intersection transformation. And we have subtract where you have also two RDDs and you output all of the values of the first RDD on the left, except those that appear in the second RDD, subtract. In fact, that might not be new to you because these three union, intersection, subtract, it's kind of always the same. In SQL, for example, in SQL, you typically have union, intersection, and subtract. So these three kind of always go together, right? If you have one, you have the three of them, okay? So I think that this is probably why it's called union, intersection, subtract, because typically this is viewed in a set environment. You could have, of course, users of Spark that don't care about the order, right? The order is maintained, but they don't care about it. For them, it's just so values and they do that. Okay, here's another one that you can do. Yes, there's a question over there. Where's the catch box? Over there. Yeah.
I have a question. So because these are like technically set operations, as you said. So for example, for the union, is there any notion of like, because in a union, normally if you have like one value in both sets, obviously then in the last set, you only have the value once, but here it's literally just concatenation. There's no like sense of like eliminating the duplicate in that sense, where how it would be in set, for example.
So here, I don't think you eliminate duplicate. We will all check offline. This is actually interesting. My guess is that there is no duplicate elimination. It's just a concatenation. You just concatenate the two.
And then a similar question for the intersection.
Yep.
How do we, is there like a given like order? Because it's just random basically.
I think here it's random. We'll actually understand why later, because there is a reason for that on the physical level. I can tell you, you probably already guessed that this is going to involve a shuffle. So things are going to be shuffled around. From the moment you shuffle, you know, you kind of lose an order. But it's kind of expected, right? I mean, if you want to intersect, you probably don't expect the result to be in any specific order, right? Because it could be in a different order on the left and on the right. So yeah, the same goes for, oh, here, maybe it's interesting. Maybe you would preserve the order here. Maybe you could preserve the order of the first RDD. It's a good question. Yeah. Yes, another question?
For this subtraction, there's one blue cube on the right and 3 on the left. And in the end, you get 1. So that one blue cube takes out 2 of them.
So here the question is if it's intentional or not. This is also something I should investigate, if it eliminates duplicates or not. Yeah.
Red arrow, it seems like the one red value takes out all of the red values, but then one of the blue survives.
Yes, it's probably also that the colors are not exactly faithful. Yeah. So this is my bad. Yeah. I already tried, you know, multiple times. It's every year it's a different lighting in the room. So I try to adapt the colors in such a way that that they can be distinguished also between red and blue and so on. But yeah.
Sorry.
No, not at all. Not at all. It's really my mistake if I don't get the colors right. Okay. Okay, but I think here I don't think it eliminates duplicates. It's really just keeping whatever is not on the right. But this is also something we look into offline. Maybe I think it's almost the time. I might finish on the Cartesian product. Yes, we have a few more minutes. So this I can explain. So this here, basically, I need to add with great power comes great responsibility, because you can imagine if you have 1 billion items in the RDD that you see on the top and 1 billion items on the RDD that you see on the left, the Cartesian product is going to contain 1 quintillion items. And here, unless you're using this Colossus multi-data center architecture, I don't think quintillions is going to work in a single cluster. So you need to be very careful when you do that. I think there's even I think there is a switch in Spark. I think by default, it's deactivated. It will not let you do that. And you can activate on the command line, enable Cartesian product. Wow, 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 enable Cartesian product. But if you do that, your own responsibility. If you crash the cluster, then it's your problem, right? Or the problem of the sysadmins of the cluster. Okay. Yeah, that's the Cartesian product. Okay, I think I'm going to end here, right? So we saw the transformations and we'll look at the actions first time next week. So all the things you can do to collect, for example, the data to your client or write them back to HDFS and so on. So I'm going to recheck whether you followed and let's see if it's better than yesterday. Yeah. I have to again open the question. Here it is. So tell me. And you know, you can always ask questions offline. You can write to the TA team. You can write to me directly. You can write on the Element chat, on the Moodle forums. Oh, this is beautiful. Okay, awesome. Okay. So thank you very much. Thank you, Matt, for moderating. Enjoy the exercises on Dremel and so on. And then I'll see you next week on Tuesday at 2 for the continuation of the Spark lecture. Goodbye.